Welcome to the talk series. They were getting a late start this semester. Had a bunch of things and the new computers and things. We had a new screen. It's my fourth talk this semester, so stay tuned. And without further ado, let's give a warm welcome to Mr. Fred Buls from our Clarkson campus. And he's going to talk to us today about LADEE, which is the newest moon mission that just got off the ground before the government shut down. So it's so important.
Thanks. Yeah, LADEE stands for Lunar Atmosphere and Dust Environment Explorer, and it's a probe that's orbiting the moon right now. It's been there for 2 weeks or so. And its purpose is to study the very, very thin atmosphere that the moon has. The moon, a lot of researchers that study the moon's atmosphere don't even call it an atmosphere. They call it an exosphere. A layer of an atmosphere that's so thin that the molecules don't even run into each other is known as an exosphere. Here in this room, the density of air is something like 1 million particles per cubic centimeter, and they're running into each other millions of times per second. But in a really thin atmospheric layer, an exosphere, the particles aren't dense enough to really run into each other very much. And the Earth's upper atmosphere, like above where the International Space Station is orbiting, is called its exosphere. And those particles don't even hit each other. They just kind of bound out from the lower atmosphere and arc over and down back into the lower atmosphere. That region is known as the exosphere. And the moon doesn't even have enough gas to have any other layer other than an exosphere. So the total mass of it is maybe half a ton. Total mass of the Earth's atmosphere is like 6 quintillion tons. So it's very, very different. But it may be a more common type of atmosphere because there are a lot of small bodies, smaller bodies like the moon in the solar system and presumably in other planetary systems that don't have enough gravity to hold on to a significant atmosphere like we have. And so it may be a fairly common type of atmosphere. Okay. We know there is an exosphere there because there's several lines of evidence. This is a photograph taken by a lunar probe, and the sun is over the horizon here, and you can see this glow. Some of this might be the corona of the sun, but it's probably also scattering from the gases in the moon's exosphere. Go ahead. Now, this is one of the Surveyor probes. I think that's a photograph of one on the Earth, but the Surveyors were landed on the moon. They were unmanned probes, landed on the moon in the 60s prior to sending people there. And they took photographs. The astronauts were only there during the day, but these things were there at night, and so they took photographs of the horizon just as the sun was coming up, and you can see the glow on the horizon. Now, this is probably scattered from material that's really close to the surface, maybe just within a few feet of the surface. LADEE will be interested in material that's farther up. Okay. These are drawings made by Gene Cernan, who was the commander of Apollo 17. When he looked out the window when they were orbiting the moon in the command module, he saw this glow before the sun came over the horizon, and also some streakiness. And it's been a kind of a mystery since then, since 1973, what is causing this. And it's thought there might be not only gas particles, but dust raised above the surface. Now, Earth has a lot of dust in its atmosphere, but it's up there because we have a dense atmosphere, and it doesn't take much of an air current to carry dust up. The moon doesn't have enough of an atmosphere to support dust up there, so some other mechanism is supporting it. Either it's flying up from constant impacting, or it could be levitated above the surface by electrostatic forces. That's one of the ideas. And they want to check for this. Go ahead. This is an instrument. It's a UV spectrometer that was put on the moon by Gene Cernan and the other guy that landed during Apollo 17. One of the things you can do with UV spectrometry is study the content of gases. And this spectrometer was able to detect all of these gases. So that's argon, helium, molecular oxygen, like we have in Earth's atmosphere, methane, nitrogen, carbon monoxide, carbon dioxide, in very trace quantities. So we know those gases are there, but what people would like to know is how are they distributed around the moon? How does it change with time? And how much is there total? There's also been some observations made since the early 70s. From Earth, people have detected the presence of sodium and potassium atoms that have been boiled off the surface of the moon, probably through a process called sputtering, where high energy particles strike the regolith of the surface, and it releases some of these atoms. And it's thought that the moon has this tail after these. This is the sodium tail. This is not a photograph or anything. This is not real data. This is kind of a simulation. After the stuff gets boiled off the surface, the sunlight sweeps it away back into space. That's probably very thin compared to some of the gases. Right? Now, I got conflicting information in looking up this stuff, but this is probably the approximate content of the gas part of the moon's exosphere. So mostly hydrogen and helium. These two biggest 5 pieces are hydrogen and helium, which is not surprising because those are the two most abundant elements in the universe, and the two most abundant elements in the solar wind, which is probably where these gases come from. They're coming from the sun, getting somehow trapped into the moon's vicinity. But also argon-40. Argon-40 is it's the daughter product of the decay of potassium-40, which is a long-lived radioisotope of potassium, and we know that's in moon rock, so that's probably where that stuff comes from. Since it turns into argon, which is a gas, it enters the moon's exosphere, and you can see also H2O. Okay. So one of the reasons why they want to do this right now is because it's been 1976 was the last time that any mission was landed on the surface of the moon. And of course, since the atmosphere of the moon is so thin, you can't land on the surface using parachutes like you can on the Earth, right? You have to power land using rocket engines. So you come down supported on rocket engines. That's how all the Apollo missions landed, all the Surveyor missions and the Luna missions that the Russians sent up there. The last one has been since 1976. Since that time, the gases that have come out of these engines have probably completely left the moon's exosphere. So what we have now around the moon is a natural exosphere. And they want to test that, the composition of that, see how it's composed and everything before some of these missions start up again. Because most of the space agencies around the world have plans to do some sort of landing missions on the surface of the moon, either manned or unmanned. This is one that's been designed by the European Space Association, and it's a fairly big probe. And you can see when it's landing, there's lots of gases coming out of there. And since the moon's exosphere's mass is only like half a ton, you can really change it by adding more gases from even a single lander. Next. And in fact, the first one that's going to get there is going to get there in December. The Chinese have this Chang'e 3 probe, which it's a fairly large lander. It's like 2,200 kilograms or something like that. So when it lands, it's going to expel a lot of gases out of its engine. And it's got a little rover that's going to rove around for a couple of months and take pictures and everything. This is going to launch early December, and it'll land like mid to late December. So LADEE is in orbit around the moon now. It's not yet taking science data. It's not yet measuring the content of the moon's exosphere, but it will be in a little less than a month. And then a month from then, this probe will land on the surface, and this could very well be able to measure, the impact on the moon's exosphere of this probe. So here's the flight profile for this Chang'e 3 mission. Go ahead to the next. Oh, you got to do two things. Oh, okay. And here's the descent profile. So it's going to descend, powered landing like this, and there's a hovering phase. It's going to hover above the surface and take pictures. So the whole time it's hovering, it's expelling gases out of its engines, so that it should affect the exosphere, considerably. Yes, sir. Okay, here are the main objectives of the LADEE mission. And you'll notice that two of them are science objectives, learning about the exosphere of the moon. And the rest are really engineering objectives, having to do with how you send probes into space and operate them. The first one says measure the density and composition of the gases, and how do they vary as a function of position around the moon and also as a function of time. The moon has a solar day that's about a month long. In other words, it's 2-week daytime and 2-week nighttime, and the temperature is very different from one side to another. And it could be that the exosphere is quite different from the daytime to the nighttime. So LADEE is going to be orbiting day, night. It only takes about 2 hours to orbit the moon once. So it's going to be testing the structure of the atmosphere from day to night. So the gases, going to look at those, and also the same thing for the dust particles that are in the moon's exosphere. And when I say dust, they're talking about particles probably no bigger than 5 microns, 5 millionths of a meter. I was measuring a piece of copier paper. I'm going to have one here, but anyway, a piece of copier paper is about 100 microns thick, so 20 times smaller than the thickness of a piece of copier paper. That's about the largest particle that they're expecting to find of dust that's above the surface. The reason is it's thought that it's levitated above by electrostatic fields. When sunlight strikes the surface, it could very well put an electric charge on the dust that's on the surface, and the very lightest of those could be repelled enough by the electric charge to be levitated kilometers off the surface. Now, the other 3 mission objectives, they want to test this laser communication device. In the past, in all satellites and space missions, they've communicated with them by radio waves, and that works quite well. You can send a lot of data by radio waves. The trouble is, when you start going really far from the Earth, it limits the rate at which you can send data, like the number of megabits per second that you can send. And that's because it's difficult to focus radio waves into a narrow beam. And by the time the beam gets back to the Earth, if you're tens of millions of miles away, it's spread all over a large area, and you have to have a great big dish to detect enough of those radio photons in order to get a signal out of it. And that limits the rate at which you can send data. But what if you use a laser beam to send data? Laser beams are very focused, right? Like the most focused light that we can make. And if you can modulate that beam to carry data, then you can send data at a much higher rate. LADEE doesn't actually need this device because it also has a radio antenna to send all the data that it's going to collect. But this is kind of a test of a technology that they're planning to use on future missions, including manned missions, because they want to send people deeper into space than the distance to the moon. And whenever there's people on board, it tends to increase the amount of data that goes up and down from the ground for a number of reasons. So that's another mission objective. They also want to demonstrate a low-cost, yes?
I'm sorry, I know I came in late, and I know that you've been talking about LADEE. I just wanted to know, what is exactly LADEE? Is it like a machine that goes up to the moon?
Yes.
Different gases?
Mm-hmm.
Okay.
Yes, it's a machine. And so I'll show you the instruments that are on board. It is now orbiting the moon.
So it basically go by itself. There's nobody,
Right.
You don't need nobody to be in there, so basically.
Right, nobody's in it.
Okay,
There's people on the ground in California controlling it
okay.
remotely.
And how long does it usually take to get to the moon?
Well, this one took about a month. I'll talk about why that is,
Okay.
if you take longer, like with a lot of things. They're trying to go low cost on this thing. Anything you do in space is super expensive. So they're demonstrating a low-cost spacecraft architecture. The way this thing is built, it's built up from a modular kind of system, which should lower the cost of sending these science probes into space. And they also wanted to demonstrate the use of the Minotaur launch vehicle, which I'll talk about, for science missions. Yeah, go ahead. Okay, one interesting thing about this is that this is the Ames Research Center in California. NASA has a whole bunch of centers, and Ames in the past has done mostly aeronautics research. This is a huge wind tunnel. You can put a whole airplane in there and test it there in aerodynamic properties. And let's see, there's another wind tunnel here. I think that's a supersonic wind tunnel. There's one here. You can't really see it, but there's one over here, and there's one right here. It's got a whole bunch of wind tunnels. They're doing a lot of aerodynamics and aeronautical research. But LADEE was designed and built and tested and is being operated from Ames, which is sort of unusual, and it's not that big a deal for most people, but for NASA it is, for this to be involved in a science mission like this. So that's one unusual thing about it. Go ahead. Another innovative thing is this use of this module. This is what I was talking about, the modular spacecraft system. They have these different modules that they can put together in different ways and build. This LADEE looks more or less like that. But you can also build landing craft, like if you want to land on the moon. And NEO rendezvous, that's for rendezvousing with an asteroid, I guess. And so different kinds of probes can be built in the same architecture, and that should make it more inexpensive because you don't have to redesign the whole thing from scratch every time you build a probe. And it's very lightweight. Go ahead. These modules are very lightweight because the frame components are made of carbon fiber, and the lighter you can make a spacecraft, the cheaper it becomes, mostly because launching something into space is very expensive, and the heavier it is, the more expensive it is, because the larger the launch vehicle you need.
Sorry, there was a question
Okay.
online. So where in California is this?
Where is it?
Located?
San Francisco.
Oh, okay.
There you go. In San Francisco Bay Area. For those of you. So this is LADEE. This is like a year ago when it was being constructed out at Ames. And you can see the components here. These are the frame components, and there's all kinds of the hardware, electronic hardware that's inside. I'll go to the next one. And this is an example of this isn't a functional thing. I mean, this isn't going to land on the moon or something, but this is a sort of a concept model of a landing probe that can be made from this architecture. So I'm not sure when they'll actually fly one of these, but that gives you an idea of what that would look like. Okay, go ahead. Another interesting thing about this mission is that it was launched from the Mid-Atlantic Regional Spaceport, which is in Virginia, at one of these coastal islands in Virginia. And there's been a rocket launch site there since 1945, just after the war, when the U.S. started to get interested in building missiles. And they've launched 16,000 rockets there, most of which are like missile tests, rocket tests, and science missions that are just atmospheric tests. In other words, they don't go into space. But recently, they've turned it into the Mid-Atlantic Regional Spaceport, and there's been more launching into space from there. I'll go to the next one. And this is just a blow up. You can see DC right there, and here's Richmond. Gives you an idea where it is. And these coastal islands, one of these, I think this is it, Wallops Island is what that island is called. So here's the launch facility. And this launch pad right here is where LADEE took off from on its Minotaur 5 rocket. And this pad, this is another launch pad. Both of those are used by a company called Orbital Sciences, which is a aerospace company. One of the things they do is they launch things into space for various customers. From this pad, they launch a bigger rocket that they have called the Antares rocket, and that's been in the news recently because Orbital Science has been contracted to do supply runs to the International Space Station. You know, there's a space station overhead with a fairly permanent crew of 6 people, the research lab, and it's being run by 4 different space agencies, including NASA. And what they're doing now is it has to be supplied, right? They're doing it now with private companies instead of doing it in-house. NASA has always used private companies to build things and to run things, but now it's more like they used to sort of oversee the operation of everything. Now it's more like, you know, we need to get this pallet of material up to the station, so build a rocket and a spacecraft and a launch pad, and we'll pay you to launch it into space. The idea is that it'll be cheaper that way because private companies are in business to make a profit, right? And that constraint is not really, that doesn't really constrain the way a federal agency works, right? So private companies tend to do things more cheaply. And that appears to be the case, that it is cheaper to do it that way. Orbital.
Quick question. This is a barrier island, right?
Yeah.
Do they have any hurricane protection plans or?
Yeah. Yeah, in fact, let's see. One of these was on the pad when a storm came in, and I can't remember what they did.
Okay.
Maybe they took it back to these things are built in these warehouses and then taken out to the pad horizontally and then uprighted. Seems like that was an issue at some point.
Yeah, I can imagine.
Yeah, they definitely, I mean, it's not as bad as Florida, I guess, but they do have storms out there. Okay, go ahead. And this is the LADEE launch vehicle. It's a Minotaur launch vehicle. And it's not really that big compared to a lot of launch vehicles. These are people right here. There's a person, another person. So it's only about 80 feet high, which, you know, it's a big machine, but that's fairly small for a launch vehicle, which makes it more inexpensive. And the most interesting thing about it to me is that it is a reconfigured ICBM. Do students these days know what ICBM stands for? What does it stand for? Intercontinental Ballistic Missile. It was built to carry nuclear warheads to the Soviet Union. It's a reconfigured peacekeeper missile. They were retired in 2005, and Orbital Sciences now has about 60 of them, which they intend to use in their business of launching things into space.
If they're trying to make this cheaper, will that affect the efficiency of the actual
machine?
Yeah.
The more money you have, the more capability you can put on the probe.
So the bigger it is,
yeah,
the better.
Well, one example of how more money will help will come up later.
Oh.
But you know, the total price tag of this mission is like $280 million, which is a bunch of money. But you know, that comes out of NASA's budget, of course. So the cheaper they can do it, the more interesting science missions they can fly, right?
Because the objective of this machine is breaking big data, right?
Yeah.
And if the machine is small, but due to the controller, he's not really in there. He's somewhere in California.
California.
Exactly. So I'm trying to figure out how size of the machine how will it affect, you know, because at the end of it, the machine is just there to take data, but eventually it's coming up to the controller.
Mm-hmm.
I'm trying to figure out why would it matter the bigger the machine is.
Yeah, I mean, with unlimited resources, you could definitely do more. I mean, you could have more science instruments on board, detect different things. You could have the mission last longer. That's the constraint I was referring to before. It's always a trade-off, and there's a lot of creative people figuring out how to do the most with limited resources. Did you have a question?
Yeah.
Yeah, Cassini was one of the last. He was talking about the Cassini probe, which is orbiting Saturn, and it's been there since 2004. Very elaborate probe. It's huge. Weighs like 7 tons. Probably wouldn't even fit into this room. Well, yeah, I'd probably fit. But it's enormous, and it was very expensive, and cost a lot of money to send to Saturn. But it'll probably function until at least 2017. But there's very few of those anymore. These really high price tag missions. That was billions all by itself. Okay, good. This is a Peacekeeper being in a test launch coming out of its underground missile silo sometime back in the 70s. So this is what the ICBM looked like. Go to the next one. And this is the business end of an ICBM. These are nuclear warheads. There was a type of warhead called a W-76 warhead, which is about a 300 kiloton warhead. And the Peacekeeper could carry as many as 10 of them for a total yield of 3,000 kilotons. That's about 190 times the yield of the Hiroshima bomb. So these were extremely powerful weapons, and they've been retired now. And I think it's pretty interesting that we're now using them to explore space and take data that all mankind can see instead of having them sit in the ground. One of the things when you buy weapon systems, you pay a lot of money for them and you hope you never use them, right? Wouldn't it be nice if you can somehow use those things? Here's the warhead. This is the bus stage when it comes out of the atmosphere and sparks over to the Soviet Union. And that bus stage manages the deployment of the 10 warheads so they can hit different targets. The Peacekeeper was a 3-stage missile. Here's the first rocket stage, second stage, third stage. And you can see from here on down, these are the 3 Minotaur vehicles that Orbital has used to launch things into space. And adapted basically the same from here on down. And so they add to that additional stages because a missile is not intended to put something into orbit, right? It's intended to just lob it over to somebody else's continent. And if you want to put something into orbit, you need more speed than that. So they add additional stages. And right there is a smaller rocket stage. This is called the Minotaur 4. Here's the Minotaur 4 Plus. The 4th stage is a bigger rocket. And the Minotaur 5, which one is LADEE, is a bigger one, and then a 5th stage. And I think it's just one each of these. So it's a 5-stage solid propellant rocket. Okay, go ahead. And they have other configurations that they might build too if they have customers for it. So here's the launch of the Minotaur 5 carrying LADEE. The rocket exhaust that comes out of these solid propellant motors is extremely bright, and its trajectory flew at so millions of people along these. This is our city, and you thought you wouldn't see it. Left shutter, a bright light across photographic plane made a streak on there, but it was very visible all along the East Coast, so it was visible to millions of people as it was launching. Okay. Now, when the Minotaur 5 had done its job, LADEE was in orbit around the Earth in a very elongated orbit. Here's the Earth. and here's the moon. And this was the initial orbit. The way LADEE went to the moon is on a relatively low energy trajectory. There's different ways of getting to the moon. When they sent the astronauts to the moon during Apollo, they couldn't take a month to get there, right? Because there's people on board. So they did one big rocket burn. That takes a lot of propellant, and you got to launch it on this gigantic launch vehicle, which is extremely expensive. A more cost-effective way to do it is to take less propellant and do these kind of little bursts and increase the size of your orbit into these, I think they call them staging orbits. Every time you go down here, you do another burn, and it makes the orbit larger until you're out at the moon. So go to the next one. I have several slides that have to do with this. So here's the first orbit, took 6.3 days, and then it came by the Earth, did another rocket burn. The next orbit took 8 days, another rocket burn, 10.4 days, another rocket burn, and then it went into orbit around the moon. So it took the better part of a month to get there. And if you could, that first image I showed you, that was like having the moon off to the right. But of course, the moon is orbiting the Earth. So if you show it in a still reference frame where you're standing still above watching the moon, this is the actual trajectory. So kind of a circuitous path reaching the moon. Okay. And so when they came toward the moon, they did a slow down rocket burn here, which put it into these initial orbits. And they keep doing additional burns to make the orbit smaller and smaller. I think it's presently 250 kilometers above the surface, which is smaller than these orbits. The moon is about 3,000 kilometers in diameter. So these initial orbits are very large, and they've been lowering the orbit to get it closer to the surface. Most of the moon's exosphere is close to the surface, so they want to get down as low as possible in order to sample the densest part of it. Okay. Now, one of the things about the moon is it's actually difficult to orbit at a low altitude because the gravitational field of the moon is not very symmetric. Gravity is generated by mass, right? Wherever you have mass, you have gravity. And the moon's mass is not, it's pretty well spherical, right? But the mass distribution inside the moon is not perfectly spherically symmetric. There are these lumps underneath the surface where there's a greater density of mass. And so the gravitational field is not very symmetric. So as you orbit at a low altitude, it's constantly altering the orbit. And, it constantly changes the orbit. So eventually, unless you manage the orbit with rocket burns, the probe will eventually crash into the surface, which will eventually happen when they no longer have propellant. But you can see how uneven the gravitational field is. This is the acceleration due to gravity on the moon. On the Earth, what's the acceleration due to gravity on the Earth? 9.81 meters per second squared. On the moon, on the surface of the moon, it's only 1.6 because the moon's much smaller, about a sixth of what it is here. But you can see it goes from 1.611 all the way up to 1.636, which is like 1.5% difference from the strongest to the weakest place. That's about 3 times as much as the variation on the surface of the Earth. So it actually varies quite a bit. That makes orbiting the moon at a low altitude relatively difficult. And to show you how difficult, I put this nasty diagram in here, but I want to explain what this means. The horizontal axis here is time, and I think every one of these is 5 days. So every thing in here is 5 days. The blue what the apoapsis at that time. So here's orbit. Apoapsis is farthest surface in the orbit. Periapsis altitude is the closest from the surface. Right? So when they're the same, that means you're in a circular orbit. But I've got it drawn here where it's a more elongated elliptical orbit. But when they're the same, that's a circular orbit. So when now they're in here somewhere in this phase right now. when they put it into orbit, the periapsis altitude was the same as the apoapsis altitude at 250 kilometers. They put it into a circular orbit. But you can see those have changed, right? And they'll change in this sort of complicated way. That's because of the uneven distribution of mass in the moon, the unevenness of the gravitational field. So the gray line, by the way, is what? Altitude at sunrise. In other words, when it comes over the edge of the shadow from day to night. So it varies quite a bit. Now, when it drops down here, what do you think is happening where it suddenly goes down to a lower altitude? Remember, this is 5 days, so this is many orbits. It only takes about 2 hours to orbit the moon. So why would it suddenly drop down to a lower orbit? They've done a rocket burn. They've adjusted the orbit to move it down to a different orbit. And you can see this is, I think it's November 11th, they'll do this burn. And they'll lower it down to about 50 kilometers above the surface. That is the the periapsis altitude. To do that, when it's over here, you do a slow down burn. And when it gets over here, it's closer to the surface now. And to lower this altitude, apoapsis altitude, you do a slow down burn over here. And by the time it gets over here, it's at a lower altitude. So, and you can see they're going to lower the periapsis altitude here, and then like 5 days later, the apoapsis altitude. And you can see once they do that, then they both start to vary, because it's in a low, strong gravity, and the gravity is variable there, and it starts to really vary a lot. And every time there's an abrupt change here, that's when they do a rocket burn. They have to adjust the orbit, or they'll crash into the surface. Because if this drifts down to 0, you're on the surface and blam. But of course, there's only so much rocket propellant on board, and so there's only so long they can do this. And this graph, the reason this graph is so complicated is because there's two things graphed here. Altitude is a function of time of these various parts of the orbit, but also the amount of delta V that they have left in there. Delta V means a Greek letter delta, and then a V means the change in velocity. You know, when you put a delta in front of a variable, it means the change of. I got some engineering students here. So the delta V, the total amount of change of velocity that the probe has on board when it gets to orbit, is about 190 meters per second. That's all they have. It's limited because of the limited mass that they could carry on the Minotaur 5. So that's an example of what you get for a higher price launch vehicle. You could have much more delta V, and you could stay there longer because you have more rocket propulsion, and you could adjust the orbit for a longer time. That line, that black line, is maximum. That's when there's maximum delta V. You can see this is where they're inching their way up, doing the rocket burns. They're inching their way up to that maximum delta V. Get up that line, they're out of position, and then gravity is going to drag you into the surface. So, the total mission is only like 100 days because of this limitation here. But it's designed that way, and they feel, I guess, that they can get enough scientific information in 100 days of reading. Okay. So here's the probe, and the way it's designed, one of the interesting design features is that solar panels, the blue things are solar panels for power. Instead of making big old like wing-like solar panels need to be aimed at the sun all the time, they just put solar panels all the way around this. Makes it simpler and cheaper, and it can be in any orientation in producing power. And I guess they have to use different orientations of it in its orbit in order to do the science things. But you can see, so here's the rocket engine. There's where the propellant is stored. So relatively small propellant things. And you can see some of the hardware. These are the three science instruments, NMS, LDX, UV, and here's the laser. I'll talk about each of those. And star tracker, this thing has to know which way it's oriented in space, and the way it does that is by finding a star of known position, and it knows which direction that is, so it can find its orientation in space. Okay, go ahead. Now, let me talk about these three science instruments. One is the neutral mass spectrometer. So, for those of you who are chemists, you may have heard of this type of a device, because this is to probe the content of the gases in the atmosphere. So a spectrometer gives you a spectrum of something. Usually when you talk about spectrometer, you think of light, but you can make a spectrum of sound. This makes a spectrum of what type of gas particles are in the exosphere of the moon. You know, molecular oxygen, atomic oxygen, molecular hydrogen, atomic helium, whatever. So, and neutral mass, in other words, just neutral atoms. And the way it works is pretty interesting. And this is, I guess these are pretty common in chemistry labs. It's called a quadrupole ion spectrometer. What happens is, I guess this is pointed ahead in the way that the thing is flying around the moon. So the gas particles coming through here. This has a large electric field across it, so electrons are spraying across, and they slam into these neutral gas particles, like, say, an oxygen molecule, and knock an electron off, which now makes it an ion. It has now an electric charge, because that oxygen molecule has too few electrons, so it has a positive electric charge. And this is a quadrupole electric field. There's 4 of these bars. I'll go to the next. And 2 of them are positively charged, and 2 of them are negatively charged. It makes this type of electric field is called a quadrupole electric field. And so they put a DC voltage on this, and also a very high frequency AC voltage. And the way these, I didn't quite figure out how this works, but this is a pretty common type of gas spectrometer used in chemistry labs. Depending on the ratio of the AC voltage to the DC voltage, for a given ratio, an ion of a given mass will stably spiral down the axis of this and make it to the other side. And all the other masses will be in unstable spirals and fly out of there. So what you do is you set that AC to DC ratio at a certain level that chooses, say, oxygen ions. And the particles make it to the other end of those 4 rods, and whatever hits the detector, that's an oxygen ion. And then you change the voltage ratio for the one that chooses helium ions, and then the counter counts those, and so forth. So you go through the range of ion masses that way. That's conceptually how these things work. So it's a pretty common type of gas spectrometer in laboratories. Okay. There's also an ultraviolet spectrometer, so this detects ultraviolet light, photons, and this is another way of detecting gases in an atmosphere, but the neutral mass spectrometer detects the particles that actually come into the probe. This detects light that is scattered off of the gas particles. They're not scattered, it's absorption. Anyway, it's sunlight that comes through the gas and leaves features of the gas in the spectrum. So this detects gases in a long column in the direction toward the sun from the probe. So both these instruments are to detect gases, but they detect different things. One of them in the probe and the other along a long line of sight. Okay. And this is the dust particle detector. There's dust particles in the exosphere too, presumably. And when a dust particle comes in, it's got this hemispherical thing with a strong electric field from this electrode to this one, so a radial electric field. When the dust particle comes in and slams into here, some electrons come off and also some ions. The ions are attracted toward one pole of the one electrode of the electric field, and the electrons toward the other, and that gives a pulse of current. And from the properties of the pulse of current, the properties of the dust particle can be inferred, like the size of it and how fast it's going, and I guess maybe something about its composition. I'm not sure exactly what they can tell from these things, but basically they want to find the what size dust particles are above the surface and, what direction they're moving and stuff. Okay. And then finally, the lunar laser communication demonstration. So it has a laser on board that's going to beam the signal down to this receiving station on the ground. Go ahead to the next one. So this is one of the receiving stations. So it's like a little bunch of little telescopes that pick up the beam. And I guess they've just, yesterday or the day before, just started to test this. So it's now these receiving stations on the ground. I'm not sure if they've sent any data with it. But if you look at some of the antennae they use to get data from these really distant probes, they're enormous. These giant radio telescopes, expensive and expensive to build and to operate. But this thing is, well, I wish I had a person there for scale, but it's fairly small because the light is focused. Now, the way you send information with a laser beam, you have to, I bought the cheapest lasers I could, and I'm paying for it. Okay, so I'm modulating the beam, right? And I could use Morse code or something. Maybe I can do it this way so people out in Wimboland can see it. I could use Morse code and send information this way. And if I had a bright enough laser pointer, I could probably point this at a ship at sea that's 20 miles away. And a person could probably see it naked eye, and you could, by modulating that beam, you could send Morse code or something. Okay. Well, anyway, I'm flashing a laser beam anyway. Can you see that?
Yeah, a little bit better, I think.
Okay, so if you can modulate the beam, turn it off and on, you can send information that way. So how do you modulate the beam to send 500 megabits per second? I can't do it that fast with this, right? But the way that's done is pretty interesting. I guess there's a number of ways to do this. The optic fiber communications thing, which are now very prevalent on the Earth, use laser beams, I guess, to modulated laser beams to send data. And I'm not sure how those work, but the one in here, go ahead. You have a constant laser beam that's on board the probe. It goes through a beam splitter, which is like a half-silvered mirror. Some of it goes straight through, some of it reflects off. One beam goes through a crystal with a constant index of refraction. Now, the index of refraction of a transparent material is a measure of how fast the light wave goes through it, right? Refraction, like when light goes through a prism, it changes direction. The reason it does that is because it changes speed. So the index of refraction of a material is a measure of how fast it goes through that material. So this has a constant index, goes slow through here. But this other crystal has a variable index of refraction. Certain crystals, you can alter the index of refraction in different ways. This one, if you expose it to an electric field, it alters the index of refraction. So let's say you put an electric field on there slowing down this one beam, then when the two get to the other end, they're not going to match up. Go to the next slide. So here I've got two waves. Here, when they get to the other end, if the waves are in phase and they're added back together, then they're going to add up to a taller wave, right? Because when you add a wave, if the peaks are aligned, then you get a taller peak. But if they're out of phase, half cycle out of phase, then it adds up to nothing. So if you can lag one beam behind the other half of phase, then you're basically switching off the laser, right? So, and it turns out that in this device, it's possible to vary the electric field billions of times per second. And so the feed coming into the electric device that has the electric field has the signal, in other words, the data that you're trying to send down to Earth. So there's a fast varying electric field in that crystal, which is very quickly altering the the index of refraction, and switching on and off the beam very, very quickly like that. Mm-hmm. Yeah. It would be just like, I mean, what you'd see is just like this. But you don't have to actually switch on the laser on, because I guess lasers take just, milliseconds or microseconds to actually fire up and get a population inversion and be a laser, right? So you can't really switch it on and off directly that fast. But you use this tricky optical method, and you can modulate it billions of times a second. I think this thing will have a data rate of 622 megabits per second. So I guess probably 622 switchings per second, million switchings. And that's coming down. Going up, it's smaller than that. I guess because the detector on board the probe is not as sensitive as the detector on the ground, or something like that. But so this is a very high data rate for a space probe, and so this technology should make it possible to send like lots and lots of data from a probe. I mean, they could do things like, what I wish they would do is have like an IMAX camera on a rover on the moon, so we could all like be on the moon, right? But that would take a huge data rate, right? And this is the kind of technology that might make that possible. Did you?
Is the downlink, is the downlink station on the surface, or are they beaming to the satellite?
It's on the surface. Yeah, that photograph that I showed you is it's at a NASA center somewhere. I can't remember. Maybe it's at Ames. I can't remember where it is, but I'm pretty sure it's in a NASA center somewhere. It's basically a bunch of little telescopes. All right. So this is what LADEE probably looks like in orbit. So I think it's November 11th that they put it down into its science orbit, its orbit where it'll actually begin to collect data, and then we'll see what happens.
On that note, let's try in. And do you have any questions?
Mm-hmm. Not impossible to orbit, but more difficult. Yeah. Yeah. If you're going to orbit at a low altitude, because it's going to be down at like 50 kilometers, and it's going to go even lower than that for part of the mission, because they want to sample the exosphere as close to the surface as possible, because that's where most of it is. Like in the Earth's atmosphere, it's densest at the surface, right? So they want to get down as low as possible. It's only possible to go so low without it being unsafe for the probe. But yeah, there's only a certain amount of propellant. I don't know if you missed that slide, but it shows how the orbit will be changed over time and how they're progressively using up propellant. So this has only got 190 meters per second of This has got 190 meters per second of delta V. The LRO, the Lunar Reconnaissance Orbiter, which has been orbiting the moon for a couple of years, has its original amount was 1,300 meters per second, because it had more propellant, because it was launched on an Atlas V rocket, which is much bigger and much more expensive. Yes. Did you see this one? Yeah. That's the management of the orbit. Ultimately, hopefully. It's so expensive to go into space, to do anything in space, mostly because of launching off the surface of the Earth. Well, I mean, people are talking about all kinds of stuff. I mean, they want to do space tourism. There's a company, what is it, Bigelow, they want to have these inflatable space stations where you can go on vacation. I mean, you still got to be pretty wealthy to go up into space, even if it gets quite a bit cheaper. In orbiting another star, you mean? Yeah. Well, it's not just like the Earth. And of course, there's a lot we don't know about it because we're talking about a thing orbiting another star. I mean, millions of billions of miles away. Someplace that we can't ever really go in any foreseeable future. But, it's not, the ones I know about so far are, not exactly like the Earth for sure, but we don't know.
Actually, before we get off the tangent, there's another question with students online.
Okay.
And she's wondering, are all operations managed by control operators on Earth, or are they pre-programmed?
I'm not sure how autonomous the thing, if it can make any of its own decisions. I mean, it seems like they pretty much do everything from the ground. There isn't really much that's pre-programmed. I think it's pretty much completely operated from the ground.
Well, there's not much of a delay.
Yeah, it's only, right,
yeah.
to the moon. Yeah, it's not like being out at Neptune where you got to wait a long time.
Yeah, that's actually another question that I wanted to ask. Since this new data transfer with the laser signal is being tried out, well, how far away can a probe be, and is this method still be applied?
That's a good question. I don't know the answer to that, but I haven't read that much about it. They're talking about deep space missions with this stuff because that is the thing that makes it hardest to send data over these really long distances. And I'm pretty sure they're talking about like the outer planets.
Wow, yeah, it's like they're still picking up data from
Voyager, yeah, I know. But it's one of these gigantic antennas,
You described the properties of radio waves and light, so that breaks the transceive data. I think with the Voyager, actually several hours, 10 hours.
Yeah.
Even when it was in Jupiter, hours.
Yeah, it's like over 20 light hours now.
Yeah, with the laser, I think at the distance of Jupiter, it would probably be a few minutes.
Well, all electromagnetic radiation travels the same speed in space, so it wouldn't take any more. It wouldn't get any faster, but more of the photons that it emits would get to the receiver. Yeah, it's you can't do anything about the time. Speed of light that's as fast as it goes, and all radio waves, X-rays, visible, it all travels at the same speed in vacuum.
Okay, as long as there are no more questions, then let's thank Fred again.
Thank you.